that magnetic fields are created by moving charges. So moving charge creates a magnetic field. So charge moving in a conductor creates a magnetic field. A charge moving on its own creates its own magnetic field. So by that logic, every electron orbiting a nucleus should create its own magnetic field, and that is exactly what happens if you get to third year electromagnetism or electrodynamics as we call it. You will understand and will calculate the magnetic moment of an electron. Okay, now that is the summary of what we'll be doing today. We know that electric fields are created by moving charges, and this is usually calculated using something called the Biot-Savart law, but there are variations of this law. It's the same law, but it's been simplified for different type of situations. Now, for a current carrying conductor, okay, for a current carrying conductor, we know that the magnetic field for a current carrying conductor, that the magnetic field for a current carrying conductor is equal to the permeability of free space multiplied by the current divided by 2 pi times the distance away from the current carrying conductor. Okay, if say this is the current carrying conductor, there we have the charges flowing in it, current is flowing in that direction. The electric field, according to the right hand rule, will be in perpendicular circles around the current carrying conductor. If it's in that direction, using our right hand rule, we can show that it will be in this direction will the magnetic field be flowing, be magnetic field, okay, where the distance from the center of the conductor to the magnetic field itself is r. And then the permeability of free space, of course, has a value of 4 pi times 10 to the negative 7. That is the permeability of free space. Now, this is all you need to understand today's class or tutorial session. Okay, let me just check all my mics and stuff are operating. Yes, so I haven't been speaking to myself. Okay, so let's start. Switch on my mic there. Sources of magnetic field. So sources of magnetic field. Sources of B fields. I will describe it as B fields. Sources of magnetic fields. Okay, so sources of magnetic fields. Now we've already established that magnetic fields are caused by moving charge. Okay, magnetic fields are created by moving charge. Magnetic fields are created by moving charge. Now, if you do not believe me, you can go read up about it. Let me just check something. And I wanted to actually show you, let me just show you here. I'm going to write here where the question is, you'll see there. I just switched to a searching tab. What causes magnetic fields? Now, like I've said before, magnetic fields are simply created by moving charges. And there it says there, magnetic fields are produced by moving electric charges. Okay, so moving electric charges creates a magnetic field. And I just thought of something. Let's see, there is a magnet there. Well, I've learned this before. If a magnetic field is caused by a moving charge, then By that logic, every magnet must have moving charges inside of it, and the Earth, having its own magnetic field, must have moving charges inside its core. So the motion of electrical charges causes a magnetic field. Now let's go to some questions regarding the sources of magnetic fields. Some general questions which you should know and be able to answer. Let's see. Question number 1. This question simply asks, consider a long, thin, straight wire with a current I. So consider a long, thin, straight wire with a current I. So there's a current flowing in this wire, and that current is I. Which of the following statements about the magnetic field lines are true? So let's go. If this current is flowing on this wire, the magnetic field lines would be perpendicular to this wire. So they would be, I'm trying to draw it, but I'm not a good artist. So it'll look something like this. It'll be centered. Let me try and draw it this way. So this is still question number 1. I'm going to try and draw the magnetic field first. This would be the magnetic field. Okay. And this would be the current carrying conductor. This is the magnetic field. If the current is in that direction by the right hand rule, the magnetic field will be in this direction. Okay, so there we have a current and a magnetic field around. Now this magnetic field, now although I can't show it here, this magnetic field is perpendicular to the direction of current flow. Okay, if the current is flowing in this direction, the magnetic field, the plane of the magnetic field will be in this direction. It will be perpendicular to the direction of current flow. So let's continue. Which of these statements will then be true for the magnetic field created by this thin conductor, this current carrying conductor or wire, whatever you choose to call it? Okay, so A, it says the field lines are parallel to the wire. No, the field lines are perpendicular to the wire. So A, it cannot be A. A, wrong. B, let's see B. B says the field lines are perpendicular to the wire. Yes, the field lines are perpendicular to the wire. The field lines are directed radially away from the wire. No, the field lines are not directed radially away. By radially away, we mean that the field lines are pointing outwards from the conductor, which is not the case. So the field lines are not pointing radially away. So the field lines are not pointing radial away. What is D? It says the field lines are circles centered on any point on the wire. That is true. The field lines are circles, as we've established here, perpendicular circles centered on any point on the wire. Those are the electric field lines. Okay, so B and D are correct. Let's see, B and D. Options B and D only, they are correct. And let me just do something here. I want to erase my previous answers. Finish attempt. Submit all and finish. Submit all and finish. Okay, reattempt the quiz. So we've already established that B and D are correct. Let's see. B and D only. Check. And yes, it's correct. Now, question number 2. Let's erase this. Question number 2. The diagram shows a circular wire loop of radius R carrying current I. Okay, so there we have the wire, the drawing there. It is around, it's moving around. We have the current carrying conductor with the wire moving around. That point there is the furthest away from you, while this point is closest to you. So this wire is the magnetic field around this circle represents the magnetic field around the wire. Now if you had to look at it from the top, it would look like the top view is given there. I can't draw it better, so let's just use the drawing there that's been given. Number 2. The question then is, now this wire carries a current I and it creates some sort of magnetic field. Now the question is, what is the direction of the magnetic field at the center of the loop? So what's the direction of the magnetic field at the center of the loop? Okay. So that's the wire loop. We have a wire loop. Let's look at it from the top. That's the better. 2, and we have a top view. Okay? And it is moving in this direction. This direction. This is the current flowing in this wire. Now, if you were to curl your fingers in the direction in which the magnetic field, the wire is if you were to curl your fingers, the fingers in the direction of the current, and then point out your thumb, your thumb would point towards you, meaning it would come up out of the page. Okay, so if this, using your right hand rule, and you point or curl your fingers in the direction of the current, and with your thumb outstretched, your thumb will point in the direction of the magnetic field. So the magnetic field will be coming up out of the page. So it will be coming out of the page, upwards, out of the page. So at the center, it will be coming out of the page. So it will be up out of the page. Let's check. Simply using the right hand rule, that is correct. That's why you are taught the right hand rule at the very beginning. So up was the correct answer. Question number 3. They say 2 long straight wires cross each other at a right angle. Okay, so 2 long straight wires cross each other at a right angle and each carries the same current I as shown in the figure below. Okay, which of the following statements is true regarding the total magnetic field due to the 2 wires at the various points in the figure? More than one statement may be correct. Now let's look at this. Okay, so first we have this conductor carrying the current in this direction, and then we have a perpendicular conductor carrying the current in that direction. Now I call it conductor, you can call it wire, it doesn't matter. Now let's look at the conductor going up. I wish I had another color. I think I can change the colors here, just don't know where. Here maybe, here. Okay, that's more apps. Back. see here. No. Okay, here we have the colors. Okay, so let me just erase this one. Let me rather erase both. Okay, so we have, let's see, let's take red. Okay, so we'll have one of them as red, and let's draw the other one blue. Other one is blue. Okay, and the arrows pointing in the directions of the currents. Now let's do what they asked us to do, which is to determine the magnetic fields in each one of these regions. So this is region A. So region A. Okay, let's use green to denote the regions. Okay, so region A. We have B, C, and D. C. Okay, now I'm going to use the color red to denote which direction the magnetic field is pointing towards. Okay, in each of these regions, just for the red one. Okay, this is just for the red one. Let's go for, if we point our thumb in the direction of the current, our fingers, our curled fingers, would point in the direction, or would curl in the direction of the magnetic field. Using this, we see that the magnetic field comes out in red. It comes out at A, comes out at A. It also comes out at B. However, the magnetic field goes into the page. It goes in to the page below the x-axis. Okay, so it goes in at C and D for the red one. Now let's do the exact same thing, but for the blue. For the blue current carrying conductor, or the wire, blue wire. Pointing our thumb in the direction of the current, our curled fingers will point in the direction of the magnetic field, and we will see that the magnetic field goes out of the page on the left hand side. So it will go out of the page here, and it will go out of the page here, and it will go into the page on the right hand side, into the page on the right hand side. Okay. Now, since these current carrying conductors conduct the exact same current of I, and these points are the exact same distance from both of these conductors, we have that the magnetic fields at point A, where one comes out and one goes in, cancels out, because magnetic field is a vector, and if we add these vectors together, out and in will cancel each other out. So the magnetic field in total here will be 0. So the magnetic field here at A will be, let me choose another color to write the actual magnetic field. It will be 0. So the magnetic field will be 0 at A, and it will be 0 at C, because the magnetic fields coming out of the page at that point and the magnetic fields going into the page will cancel each other out. So at A and C it will be 0. However, at B and B, both of the magnetic fields come out, so it will be double. Okay, so it will be double here. And at D, both of the magnetic fields going in, so it will also be double, but going into the page. Okay, now let's look at what they have given us, these statements that they gave us. The first one, the first statement is the field is out of the page at point C. The field is out of the page at point C and out of the page at point D. Okay, so let's go to point C. Point C, the magnetic field is 0. And out of the page at D, there it's into the page there. So this is wrong. Statement number 1 cannot be correct. Statement B. Statement D. Statement B, actually. The field is strongest at points A and C. No, the field is 0 at A and C. Number C, or the third option, the field has the same magnitude at all 4 points. That is not true. It has different magnitudes at point A and D. And point number D, the field is out of the page at point B. Yes, it's out of the page. And into the page at point D. So number D is correct. And the field is strongest at points B and D. That is also correct. E is also correct. Field is strongest. Let's check. The field is strongest at point B and D, and the field is out of the page at point B and into the page at point D. So we are correct. Okay, let's erase this question. Let's first go back to this black. Okay, erase. Okay, good. Question number 4. Here we have 3 long wires parallel to the x-axis, and they carry currents as shown: 4I, 3I, and I, where I is 20 amperes. What is the magnitude of the magnetic field at the origin? Okay, so at the origin, what's the magnetic field at the origin? Let's first redraw this whole situation. So here we have the axis. Okay, then at a distance of 3 meters away, we have a current carrying conductor, and it carries a current of I. Then at a distance of 1 meter away, or 1 meter, yes, a distance of 1 meter away, a conductor carries a current of 3I. And finally, a distance of 2 meters from the origin, a conductor carries a current of 4I. What I neglected to include was the direction of the current. For this one, it goes in the positive x direction. This one goes in the opposite direction. And the last one goes in the same direction as the top one. Okay, so let's calculate all of these currents. I just redraw what is written on that page. Now, how do we calculate the magnetic field due to a current carrying conductor? That is easy. It is the formula I gave you at the beginning of this tutoring session. It is the permeability of free space multiplied by the current, which is what we've been given, divided by 2 times the distance away from the current, which has also been given, which is R in this case. Okay, now let's calculate it for each one of these current carrying conductors. Let's call them the first one number 1, this now after that number 2, and the bottom one number 3. Let's name them in that way. I'm gonna erase it and continue here. Let me just switch back to black. There you go. So question number 4, let's calculate the current at the origin. Okay, taking into account the direction of, we must always take the direction of the current. into account. We should take the direction of the current into account. I just had a small brain freeze for some reason. Okay, so B1 is the magnetic field caused by the first conductor, and that is 2 pi r. Now if we plug in what we've been given, which is that 4 pi times 10 to the negative 7, which is, and then of course the current is 4I, which is just 80 amperes because I is 20 amperes, so it's 80 amperes. And then we have 2 pi here as a constant. What is the distance from the origin to the first current carrying conductor? It is 2 meters. Now if we work that out, if you were to calculate it, you will find that it is 8 microtesla. 8 microtesla, and it is going, let's just use our right hand rule, point our thumb in the direction of the current, and our fingers would curl in the direction of the magnetic field, and at the origin it will go into the page. So this is into the page. So we have 8 microtesla into the page. Now let's use it for B2, the second current carrying conductor. We use the same formula, same method, just the distance and the current will change. Okay, so here we have, I'm not going to write it mu naught out, I'm just going to say mu naught. We know what the value is. Now the current now is 3I, which is 60 amperes. Sorry, it should be 60, not 6. 60 amperes. 2 pi times the distance away from the origin is 1 meter. And if we go all of that, calculate it all, we have that it is 12 microtesla. So 12 microtesla. And now important, the direction. Point our fingers in the direction of the current. Our curled fingers will point in the direction of the magnetic field, and we will see that in this case the magnetic field goes into the point at the origin. Okay, into the point at the origin. So now we have 8 microtesla and 12 microtesla going into, so that therefore the magnetic field strength going into is so far roughly 20 microteslas going into the point. Now let's calculate for conductor number 3, mu naught, lower conductor number 3, mu naught times the current over 2 pi r, which is mu naught 12 times 12.57 times 10 to the negative 3 times 10 to the negative 7 times the current at the bottom one is just 20 amps over 2 pi times the distance away from the origin is 3 meters. Calculating that out gives you the following value of approximately 19 microtesla, and that is, if we point our fingers in the direction of the current, our thumb in the direction of the current, our curled fingers will point in the direction of the magnetic field, and at the origin it will come out of the page. So this will be out, 19 microtesla out. Okay, so let's rewrite it quickly. It's 8, 12, and 19. 8, so 8 microtesla, 12 microtesla, and these are both out. These are both into the point at the origin, into, and then we have 19 microtesla out of the page, out. So these two are going into the page and this is coming out of the page. So if we want the net magnetic field, at the origin. So B net, this is B1 by the way, B2, B3. Hey, now B net is then equal to, let's take into the page as negative and out of the page as positive. So into is negative 8 microtesla minus 12 microtesla, which is where the signs just indicate it's going into the page, and the positive sign is indicating it's coming out of the page, 19 microtesla. So that is approximately negative 20 microtesla. Sorry, no, not negative 20. That is negative 20 plus 19, so it's negative 1 microtesla. So it's negative 1 microtesla. No, sorry, the third one here is not 19. 19 was the actual end of it, okay? 19 was the end. B1 is equal to, it was equal to, I got it correct, 8 microtesla. B2, I just read the wrong value of here, 12 microtesla. But for B3, excuse me, B3 is equal to 1.3 microtesla. Now if you work it out, B net is equal to, where these two are still going into the page, this one is coming out of the page. So it's the same thing, I just wrote the wrong value here. 19 is the answer here. So it'll be B1 plus B2 plus B3, which in this case is the same as saying 8 microtesla plus, let's say negative still, let's keep with negative, into the page is negative, 12 microtesla here, 12 microtesla, and then out of the page is positive, so 1.3, not 13, 1.3. Out is 1.3 microtesla. So if you add all of that up, it will be negative 20 microtesla plus 1.3 microtesla, so that will be 18.7 microtesla. So B net is negative 18.7 microtesla. So that is 18.7 microtesla into the page. So 18.7 microtesla into the page, into page. So 18.7 microtesla into the page. 18.7 microtesla into the page. And 18.7 is approximately 19 microtesla into the page. So 19.7 microtesla into the page. Let's see. Do we have an option there for 19 microtesla? There it is, 19 microtesla. Let's check. Indeed, we do have an option for 19 microtesla, and it is correct. Okay, can erase that. Question number 5. Question number 5. One long wire carries a current of 30 amperes along the entire x-axis. Okay, so let me first draw the axis. Okay, so here we have the axis. This is the x-axis. Here we have the y-axis, and here we have the z-axis. Okay, so we have the axis. And I assume whoever is Ms. Baloi, you are not, I assume you are not listening because I have not shared my screen and you have not told me to share the screen. So guess you just switched on. Okay, anyway, let's see. I need to share this. Okay, so let's continue. That's being shared. While that's being shared, okay. So there I have the set of x's. Okay, I'm dealing with this set of x's, and they told us one long wire carries a current of 30 amperes along the entire x-axis. So let's change a bit. So 30 amperes along the entirety of the x-axis. Okay, so that will be parallel to the x-axis, 30 amperes along the x-axis. Just do this along the x-axis. Where that conductor carries, it's in that direction along the entire x. A second long wire carries a current of 40 amperes perpendicular to the xy plane and passes through the point 0.4. Okay, so the point is 0 on the x-axis, 0, 4 on the y-axis here. I just switch to another color, green. Okay, so 0 x-axis, 4 y-axis, 0 z-axis. So it passes through this point. So this text wire carries a current of 40 amperes. This one carries a current of 30 amperes. And this one carries a current of 40 amperes. And this one goes through this point here. Goes right through that point there, which is 0, 4, 0. And this current carrying conductor carries a current of 40 amperes, they tell us 40 amperes. So this is the situation. Okay, we have one going through the xy plane, which is perpendicular to the xy plane, and it passes through that point. Now they want to know what is the magnitude of the resulting magnetic field at the point y is equal to 2 on the y-axis. So y is equal to 2 is here. Y is equal to 2 is here at this point here, halfway between. So what's the magnetic field at that point? First, let's calculate it for the green wire. Okay, or let's do it for the red wire first, since we did draw the red one first. Now, we know there is a formula. Or let me rather just use it this way. But I really do want to introduce you to this formula. Okay, this green is not showing nicely on the page there. Let me rather change that green to, yeah, this blue. Let's see if this blue will work. Not much better. Let me change it again. Purple. Let's see, purple. Does purple work? Okay, there it goes. Purple. That current carrying conductor. That's the point. That's the point 0, 4, 0. And that conductor carries a current of 40 amperes. My forgiveness, I didn't notice it doesn't work. Okay, so we want to calculate the magnetic field at this point here. This point here that I'm shading right now. This point here. We want to calculate the magnetic field at that point. So the magnetic field at that point will be pointing in two directions. There is a normal way we can do this and a faster way we can do this. Okay, so let's do it the long way. Okay, so the magnetic field at this point, due to the purple current carrying conductor, will be B equal to mu naught O times I over 2 pi R. Okay, now if you were to work this out, you would get a magnetic field, and this magnetic field, let's first of all see in which direction this magnetic field points. It will point at that point, it will point in this direction there, along the x direction, parallel to the x direction. And that's the way this magnetic field will point at that point, the direction. So it'll point parallel to that. So first of all, we have mu naught, we have I, and in this case it is 40 amps. We have 2 pi, and the distance away from that point is 2. So it's mu naught times 40. Okay, let me just rewrite this. I want to do the math quickly. So it's 4 pi times 10 to the negative 7 multiplied by equals 4 pi times 10 to the negative 7 times 40. There we have 4 pi. So that cancels. Pi, 4, leaves us with 1. So it's 1 times 10 to the negative 7. I'm doing this roughly, Tesla. Let's see, or 0.1, 1 times 10 to the 7 Tesla. And if we do it for the other one, the red one, let's do the magnetic field for that one as well. In this case, the magnetic field will be pointing towards me along the z-axis. So it will be pointing along the z-axis. So my magnetic field will be pointing along the z-axis. And these two magnetic fields will make a 90-degree angle. So B for the red one, let's change it to red so we know that we're working out the magnetic field for the red conductor is equal to mu naught I over 2 pi r. In this case, mu naught is 4 pi 10 to the negative 7, and the current is 30 amperes, and we have the distance is 2 away, so it's 4 pi again. 4 pi. This is 1 times 7 times, by the way, times 40. This is times 40 here. I forgot that times 40. Times 40. This answer, it should be 40 times 10 to the negative 7. It should be times 40. The current. And in this case, it's 4 pi again. 4 pi because the distance is 2. It's the exact same situation here as in here, except the direction is here. For the purple wire, the direction is along the positive x-axis. Now it's along the z-axis, meaning the magnetic field is doing this. It's along there, and then it's along here, along the z-axis. It's making a 90-degree angle. That's the two magnetic fields. So this one will cancel there, so it'll be times 30. Okay, so let's see. 30. So what we've established now is that this is the magnetic field for number 5. Magnetic field along this direction, the x direction, and then we have one along the z direction. Okay, now the one along the x direction is 40 times 1 times 10 to the negative 7, and then the one here, that's the magnetic field along that direction, and the magnetic field along this direction is equal to 30 times 10 times 1 times 10 to the negative 7. Okay, so there we have magnetic fields, these two magnetic fields. Now this I only showing you the long way because I want to actually show you the shortcut. Now in order to get the net or the resultant magnetic field B res, we need to use Pythagoras' theorem. Okay, B res, we can use Pythagoras' theorem. Now we could have just started with this part. Okay, this is where the crux of the matter. Okay, we could have just started with this. Okay, and if we had started with this, we could have used this formula, say the square root of b1 squared plus b2 squared will be b res, and there we have b1 and b2. Okay, now b1 b2 squared, we could have just said this. We know that, let's say b res equal to b1 squared. We just determined it's b1 squared it's b1 squared. Now b1 is mu naught I 2 pi r squared, and b2 is exactly the same, mu naught I 2 pi r, and that's squared. Now we could have just started with this formula instead of doing it one by one. Okay, now we can take out the constants. Okay, we can square them. Mu naught 2 pi r, we can square them and then find its square root. If we take them out, it'll be mu naught over 2 pi. That's it, mu naught over 2 pi. What we're left with inside is I over r squared plus 1. This is I1 and R1, and this is for I2 and R2, the second conductor. Now if we just plug in all of our values here, where I1 is for the first conductor, it is 30 amperes, and this conductor is a distance of 2 away. We square that. The next one has a current of 40 amperes, and it's a distance of 2 away as well, as we've established before. We do this whole calculation, we will find that the answer is 5 microtesla. Okay, 5 microtesla. Let's go see if there's an option for 5 microtesla. And let's check it now. Check. Indeed, the answer is 5 microtesla. Okay. You can do it individually, and then just using Pythagoras' theorem, you can find the resultant, or you could use this formula here, which is much easier. Now, question number 6. Question number 6. Let's see. It says 2 long parallel wires. So 2 long parallel wires are separated by, so let's say here's one and here's the other one. So they are long, they are separated by 5 millimeters. So the distance between them is 5 millimeters. I always try to draw what they tell me, the information, to visualize it. So we have 2 wires, they are parallel to each other, and they are 5 millimeters apart. They each carry a current of 60 amperes. So each one of them has a current of 60 amperes. So there we have 60 amperes, a current of 60 amperes. These currents are in the same direction. So both of these currents are in the same direction. What is the magnitude of the magnetic field at a point that is between the wires, or somewhere between the wires, and it's 2 meters from one of the 2 wires? Okay, so let's say from the bottom one, 2 meters, so somewhere around here. So what is the magnetic field at that point there? It is 2 meters from here to there. Let's see, that's 2 meters, 2 millimeters, sorry, 2 millimeters, which means the distance from there will be 3 millimeters. So all we have to do now is to calculate the magnetic field from that current conductor to there and from this one to there. Okay, now if we use the right hand rule for the bottom one, okay, now we have a drawing of what is happening. Okay, now we can calculate. Let's do the calculation for the above one on top. So the magnetic field for the conductor above is going to be B equal to mu naught. Okay, let me see. I don't know if you can see that. B will be B is equal to mu naught times I over 2 pi r, and that is just 4 pi times 10 to the negative 7 over 2 pi times the radius. Okay, so how far is it from this point? It's 3 millimeters, which is 3 times 10 to the negative 3. So that's your first magnetic field. That's the first magnetic field, 3 millimeters away. And that is roughly, according to my math, should be about 4 times 10 to the negative 3. If I'm correct. Oh, I forgot here something. The current for the top one is 60 amperes. Okay. So basically this is happening. 2 times 60. 2 times 60 is 120. 120 divided by 120 divided by 3 is 40. Negative 7 plus 3, so it's negative 4. 40, if we move it away, it is negative 3. Okay, so here we have it. 4 times 10 to the negative 3 for this first one. Okay, and let's see. This one is, like all vectors, it has a direction, and this magnetic field is going into the point there. This is into the point. Now let's use a different color to calculate it for the bottom conductor. Let's use red. B equal to mu naught times the current over 2 pi r. Okay, now we know that mu naught is 4 pi times 10 to the negative 7, the same current of 60 over 2 pi. What's the distance away? In this case, it's 2 millimeters, so 2 times 10 to the negative 3. And the answer would then be, let's just check what is the direction, first of all. Okay, we point our thumb in the direction of the current. We see that at the point here, at this point, the magnetic field is pointing upwards, so out of the page, And let's calculate. That's 4 divided, that's 2, that's 120. 120 divided by 2 is 60. So it's 6 times 10 to the negative 3 out of the page. Okay, now let's take out of the page as positive. Okay, and we can do the net. Okay, so the net magnetic field. So the net magnetic field. So the net magnetic field Okay, so B net for this problem, the net magnetic field will be B out of the page minus B into the page. Now B out of the page is equal to 6 millitesla, and B into the page is equal to 4 millitesla, and that is just 2 millitesla. So it's 2 millitesla out of the page. Okay, so 2 millitesla out of the page or upwards. Okay, so 2 millitesla. Let's check. And yes, we are correct. Let's erase, switch back to black. Okay, question number 7. Let's continue. We have two very long parallel wires. Okay, we have these two very long parallel wires. They carry currents in the positive x direction. So this is the y-axis, that's the z-axis. The positive x direction goes into the page, and they are parallel to the x-axis. Okay, one wire carries a current of 15 amperes, wire number 1, and it's coincident with the axis, so it's lying directly on top of the x-axis. And the other wire is parallel to the x-axis, a distance of 50 amperes away, and it passes through the point 0, 4, and 0. So basically what it is passing through the y-axis parallel to the x-axis. What is the magnitude of the magnetic field at the point 0, 0, 3? So at this point on the z-axis P. So what's the magnetic field? Okay, so this is very easy to work out. Let's just draw the situation there. We have this. This is the y-axis. This is the z-axis. And here we have, okay, let me just change it. Here we have the first magnetic field, and it'll create a huge circular magnetic field. Let me just draw this smaller. So let me just draw it a bit smaller. I want to depict the actual magnetic fields. So here we have magnetic field source number 1, that point 444. So it'll have a magnetic field that goes through this point here, somehow like this, in a circle. It'll touch that point P like that magnetic field. Touch it like that. Then we have a purple, or the magnetic field at this point here, and it will touch that point P like this. So it will go like that. Now it's not up to scale. I just want to show you what happens at the point P. It's not up to scale. Just want to show you what happens at the point P. It's not up to scale. So it is something like that and something like that. So the magnetic field at this point here, due to the purple wire, so wire 1 will create a magnetic field tangent to the field, which is, in this case, it will be downwards. So wire 1 will create a magnetic field downwards, while wire 2 will create a magnetic field tangent to it at point P, so in that direction. Okay? And that is what's been drawn there. Okay? I just want to show you this angle here. If we were to draw it, will make 90 degrees, and this one here, if you were to draw it with that one, it will make 19 with the y-axis. Okay? The vector field lines are perpendicular to the line from the origin. Okay, so let me just where do I go out now? Okay, so this is the situation. We have a line going down, and we have a line B2 going in that direction, B2, and then we have B1 here. Okay, now what is this angle? Okay, now we know. Let me just redraw this one in. This is the axis. This is the x. For some reason I can't seem to. Okay, that's about as straight as I will go. For that line, and that's y. That's z. Okay, so this angle here, if we were to make a triangle, that's one wire and that's the other wire. Okay, using these lengths, 3 millimeters and 4 millimeters, we can establish that is 5 millimeters. So we can calculate this angle. Okay, and if you do that, you will calculate and work out that this angle is exactly equal to 53. I did write it down earlier on. I don't know. It is 53.1 degrees. I'm just going to write 53. So this angle is 53 degrees. Okay, if you use our Pythagoras theorem, the sin cos tan relationships, and work out this angle 53. Okay, now we know that this angle, this line with this one, should be 90 degrees. Okay, those two should be 90 degrees. Now if this one is 53, that means that this one here should be 36, 37 rather, 37 degrees. So this angle is 37, meaning if this one is 37 and this one here is 90 degrees, we can, by geometric methods, determine that the angle here, which is what we want, is equal also to 53. So this angle is equal to 53. This one is straight vertically down. This one is at an angle. Now, what is B1 and B2? So let's calculate B1 and B2 quickly. B1, it's for wire 1. B1 for wire 1. Mu naught. B1 for wire 1. Mu naught times the current, I, over 2 pi R. That's equal to 4 times 4 pi times 10 to the negative 7. What's the current in the wire? For wire 1, the current is let's look at the problem. For wire 1, let's go read. The current is 15 amperes. So 15 amperes for wire 1 and 50 amperes for wire 2. So 15 for wire 1, 15, and then 2 pi. What's the distance that wire 1 is away from the point P? It is 3 millimeters. So 3 millimeters. And that gives you an answer of 1 millitesla. So 1 millitesla. Now for B2, so B1 is 1 millitesla and B2, if we do the same calculations, the exact same thing, we found that it's mu naught times I over 2 pi R. Mu naught is 4 pi times 10 to the negative 7. Brackets. Then we have the current is 50. Then we have 2 pi. The distance is 5 millimeters. And we have that the answer is 2 millitesla. Okay, so 2 millitesla. 1 millitesla and 2 millitesla. Okay. So B1 equal to 1 millitesla. B2 at an angle of 53. B2 is equal to 2 millitesla. Okay. And that angle there is 53. Let's just use 53. Now, how do I get the net angle? Now, you can do the cross product, but I don't like that, so I'll just break it into components, which is easier, and I've been taught to do that. So breaking this one B2 into components. Okay, breaking B2 into its components, which I'm not going to do now. So I'll just say Bx and By. So it's X and Y components. You will find that the X component is 1,660 1,60 millitesla is the X component, and the Y component is 2,19 millitesla. So the Y component. So there you have successfully broken up this vector into horizontal and vertical components. Now if we add this to this 1 millitesla, we will get 3 millitesla downwards and 1.6 millitesla. So it will be 1.6 millitesla in the x direction, but it will be 3 millitesla, 3.19 millitesla down. That is if you add these components together. Now to get the net, you just use Pythagoras' theorem. And if you use Pythagoras' theorem for this, you will find that the answer is 2.72 millitesla. So the net vector going in this direction will be 2.72 millitesla using the Pythagorean theorem. Okay. Now, if you want to do that, you can actually just do it yourself, which is just B resultant equal to the square root of, this is 3.1 by the way, and that's 1.6. I keep forgetting this. 1.6 squared plus 3.19 squared should get you 2.72 millitesla. That is your resultant vector, 3.2 millitesla. Okay, sorry, it's 2.7. Let's check. Is it 2.7? Yes, it is. The answer is correct. Now, a straight wire of length L. Question number 8. A straight wire of length L is bent into that shape. It's been given there. So we take this wire and we bend it into that shape. Semicircle. And that's the center, the distance there. That distance is the radius of that semicircle, R. Okay. Now the length of this semicircle. Now normally the circumference of a circle is 2 pi r, but this is only half a circle, so we divide 2 pi r. The length of a circle, so the circumference of a circle is 2 pi r, but this is a half circle. It's a semicircle. It's a semicircle, so it will be this divided by 2. So it'll just be pi r. So the length of a semicircle is pi r. So the length of a semicircle is pi r. So its length is equal to pi r. Therefore, r is equal to the length divided by pi. So r is equal to the length divided by pi. So the radius is equal to its length divided by pi. Now we know that the magnetic field is equal to mu naught times the, this is from, and they ask us here, use the Biot-Savart law to deduce an expression for the magnetic field at its center due to the current I passing through it. Okay, so we have a current I passing through it, and express your answer in terms of the current I and mu naught. Okay, so here we have mu naught times I times theta. That's the Biot-Savart law over 4 pi r. Okay, this is the Biot-Savart law. Of course, it has a differential and an integral form, but I choose this form. It's easier to work with. Now we know that mu naught Okay, the same. The current in this case is I, but its angle goes from 0 to pi. So the angle is just pi for a semicircle. Okay, it doesn't go a full 360, it just goes from 0 to pi. So the angle theta is pi. Here we have 4 pi times the radius, which we've established is L over pi. L over pi. But also we forgot something, or rather I did not write it in immediately. 4 pi times 10 to the negative 7 is, oh, I don't need that. Let's just leave that out for now. We don't need to split that up. We can have just divided that, but it's unnecessary. So if we simplify this, okay, we have this canceling, that canceling. 4 is still there. That goes up. So it's mu naught times L times pi over 4. L. Still an L there. So the L does not belong there on top. It's mu naught. That's I. I and 4 and L is at the bottom. That's pi. So that is your answer to the magnetic field at the center of this loop. Let's see if one of them is in this shape. So mu naught times I times pi, mu naught times I, mu naught times I, mu naught times I times pi. So we have a contender over 4L. C, let's check number C. And indeed it is correct. Okay, we have done 8 questions so far on calculating the magnetic field due to current carrying conductors. Okay, tomorrow James or Arnold rather will continue along the same lines of inquiry, and he will hopefully explain and elucidate some things I maybe went over too fast with or you didn't grasp that well. So please tune in tomorrow for Arnold and enjoy the rest of your day. Bye.